This is section 16.6, number 2b, and we're asked to parameterize the lower half of this ellipsoid. So our first attempt, we're just going to brute force it. We're going to say our r of uv is equal to, well, we use u for x and v for y. And then, of course, we have to solve the ellipsoid for z, for its z component. And that's going to be, because they asked for the lower half, the negative square root of 1 minus 2x squared minus 4y squared. So there it is. This is a parametric equation in u and v, which would map the lower half of this ellipsoid. The problem is, what limits do we use for u and v? Because they represent x and y, you know, these are going to be pretty terrible to get for this 3D shape. There's going to be lots of square rooting, and, you know, we can evaluate what x needs to be and then look for y as a function of x, and finally z as a function of x and y. But that's all due to our choice. This is not a good choice if we want to parameterize the ellipsoid. It's easy to get, but it's really difficult to work with. Imagine if we had to take partials of this, wouldn't want to take the partial of that. So here's another way to think about it. This guy's very much adjacent. Ellipsoids are very adjacent to spheres. And a general parametric for a sphere is to use an x component of sine phi cosine theta. Actually, I'm going to make these theta and phi. That way I don't have to rewrite the variables. The y component is sine of phi sine of theta, and the z component is cosine of phi. Now, the one thing that's missing here, of course, is the radius. For a sphere, you'd throw a row into each one of these, because then that would inform how each component's based. And the advantage of this is, I know the parameters. If I want to do a whole sphere, then I know rho goes from 0 to the edge. I know that phi goes from 0 to pi, and I know that theta goes from 0 to 2 pi. So that's the advantage I have here, which I don't have here. I have very difficult parameters to gather for u and v in terms of limits of integration, but easy ones here. Of course, the problem is an ellipsoid is not a sphere. It doesn't have equal radii, but that's okay. I can fix that. So if we rewrite this, this ellipsoid as x squared over 1/2 plus y squared over 1/4 plus z squared over 1 equals 1. And all I've done is rewritten it, so the coefficients are now in the denominator inversed. Well, it turns out this is equal to a squared. So that makes a equal to radical 2 over 2. And that turns out to be the radius associated with the x component of anything associated with this ellipsoid. So that's the coefficient, radical 2 over 2. That's in essence what its rho value is, because that will be the maximum value that x takes on in this ellipsoid. Let's do the same thing for y. Of course, this is b squared. So that makes b equal to 1/2. And that's the coefficient here, 1/2. And then finally, this is c squared. C squared is 1, so c is 1. And that would be the coefficient here. And in order to see that this really does indeed replicate this function as a parametric, easiest way is just to plug the components in. So let's plug those into here and see what we get. So we're going to get 2 times radical 2 over 2 squared. Sine phi squared cosine theta squared. And then we'll add to that plus 4 times, oops, I'm going to square that, 1/2 squared times sine phi squared sine squared theta, and then finally plus coefficient of 1, z squared is going to be cosine of phi squared. And then we want to see what this is equal to. Well, radical 2 over 2 is 1/2 times 2. Those are going to cancel. So it's sine squared cosine squared, 1/2 squared, and the 4, those are going to cancel. So sine phi squared cosine and sine, this is going to make sine squared phi if I just pull out of both of those, and I factor out the cosine squared and sine squared, that's 1. And then add on plus cosine squared phi, and of course this equals 1, and what do you know? It equals 1. So this parameterization is correct because it reforms the function we're after, and that's in essence all a parameterization has to do. It has to model a function. This one models it too, it's just messier, and I don't know what the limits would be, but this one's really valuable because I know what the limits are on all of these. I would know what limits to actually plug in for phi and for theta in order to reconstruct this entire thing. That's the value of parameterization.